Now we're going to prove a theorem that says that if you're differentiable in the sense of having partial derivatives, at least continuous partial derivatives, then you are differentiable in this strange linear operator sense. And in practice, if you're given a concrete function, this is usually how you determine that it's differentiable. You don't try to write out the thing with the linear operator. You just check the partial derivatives and see if they're continuous. So we're going to grab an open set in RP. Yeah, working with derivatives in non-open sets is more trouble than it's worth. So I think we're not going to do that. Let's let C be an X, F a function from X to the real numbers. In a couple of sections, in section 6.5, we'll get it to functions mapping into RQ. Now we're going to suppose that F is continuous on X. Gradient of F exists everywhere in X. So not just at one point. We can get away with just gradient of F is being continuous only at the point C. We don't need to insist that the gradient is continuous everywhere, but we do need it to exist everywhere. Then the linear operator df of C in our strange new definition of derivative exists. So let's prove this. So first off, we're going to write down essentially this is a marginal note, or a remark, but I think it will clarify matters. By the theorem we proved, the last theorem we proved, we have that if df of C exists at all, then df of C, I can tell you what linear operator it is. It's the linear operator df of C of y. The only thing that's allowed to be is the inner product of the gradient of f at C with y. So we will go try to prove that this thing, this inner product with the gradient linear operator, we will try to prove that that in fact has the properties we need for the derivative. So remember how the derivative is defined. We've got this formula, f of x is f of C plus linear operator df of C evaluated at the vector x minus C, and then we have to add to that the norm of x minus C times f of x. For some f from x to r with big F continuous at C, big F of C equals 0. And this is what it means for the derivative to exist. So now let's start on the proof proper. Let's write down what our capital F has to be, and then we'll show that it satisfies all the properties we need it to have. So we're going to define L of y as the inner product of grad f of c with y. Since grad f of c, it's a vector, it's necessarily in Rp. L is a linear functional from Rp to R. And we're going to let big F of x, what does it have to be? It's going to be 0 if x is equal to c. And if x is not equal to c, it's going to be this following complicated thing. So it's pretty clear it's just a little bit of algebra. If little x is in our set, whether it's c or not, then f of x is equal to f of c plus L of x minus c plus x minus c norm big F of x. And also L is linear. So we need only prove that big F is continuous at C. And then we'll know that f of x is f of c plus a linear function of x minus c plus norm of x minus c times a continuous function that's 0 at c. And then we'll know that f is differentiable at c with derivative L. By previous proposition, we know the derivative is unique and all these other wonderful things. So in particular, we'll know that the derivative exists. Writing out the full proof, it's going to get a little complicated, and it sort of gets much worse if you try to write it out in arbitrarily many dimensions. So I'm going to tell you that we will prove this only in the case where p is 2. And you should be able to get the idea of why it's true, how it would work in 3 or 4 or p dimensions. It's just that the notation is kind of terrible in more than 2 dimensions. All right, now how are we going to prove that f is continuous at C? We're going to go ahead and use the epsilon delta characterization of continuity. So we're going to prove that for every epsilon greater than 0, there's some delta such that if x minus c is less than delta, if the distance from x to c is less than delta, then big F of x is less than epsilon. So our delta is going to be the smallest of, it'll turn out to be 3 numbers. Here is the first of them. By proposition 5.3.3, there is a positive radius SR such that the ball centered at C of radius R is contained in G. So continuity, we can look just inside this little ball, and that'll be enough to show that big F is continuous at C. So we're going to let X be in this ball centered at C of radius R. And now let me go ahead and draw this. Here is our point C. Here is our radius R. And here is our ball of radius R around the point in C. And then somewhere in here we've got a point X. Now notice, we know the partial derivatives. We know derivatives in the horizontal direction and in the vertical direction. So we don't want to go straight from C to X. We don't know any derivatives in that direction. We want to go this way and then this way. We want to go to this point here and turn and get up to X. And this point here, let's notice it has coordinates x1, C2, same x coordinate as X, same y coordinate as C. And I'll point out to you a fact. It's very clear from the picture. You can prove it pretty easily but just by writing down the formula for distance in R2. If X is in this ball, then this point, x1, C2, is also in the ball centered at C of radius R. And so is in G. Sorry, is in our open set X. Now we're going to use the mean value theorem, just like we did back in our equality of mixed derivatives proofs back at the very beginning of section 6.2. And I'm not going to write out all the details of the mean value theorem argument. We saw them there. So f of X minus f of C, that is this piece here in our definition of big F. This is one of the things we need to deal with. We can write this as f of x1, x2 minus f of c1, c2. And then you can write this is f of x1, x2 minus f of x1, c2 plus f of x1, c2 minus f of c1, c2. And we're grouping that like this. These two terms, the f of x1, c2, of course, cancel out. And notice that f of x1, c2 is indeed well defined because the point x1, c2, it's in the balls for radius r centered at C, so it's in X, so f is defined. And in fact, along these intervals from C to x1, c2 to X, those are also in the ball centered at C of radius X. So and remember, f is continuous and the derivatives along the coordinate axes, they all exist. So we can apply the mean value theorem. There is a T1 that's between X1 and C2. and C1, sorry. And a T2 between X2 and C2 such that f of x minus f of c, that first piece turns into x2 minus c2, and then our partial to f of x1 t2, and then we add to that x1 minus c1 partial 1f of T1 C2. So there's some point in here and some point in here where the mean value theorem works for us, where the mean value theorem applies on the little yellow interval and the little green interval. Notice this thing we've just written down, it's got some derivatives of f multiplied by x's minus c's. That looks an awful lot like this L of x minus c, which has derivatives of f in it at c and x minus c. So let's write down what that comes out to. So now we note L of x minus c, that's gradient f of c, inner product with x minus c. What's that equal to? That's equal to the first one, partial 1 f of c times x1 minus c1, and then a partial 2 f of c times x2 minus c2. And that indeed looks an awful lot like the thing we've got up here. It's just that instead of having c's inside the partials of f, we've got x1, t2, and t1, c2. So f of x minus f of c minus L of x minus c, which is the whole thing in the numerator in our definition of capital F. Just a little bit of algebra. We get x1 minus c1 times partial 1f of t1 c2 minus partial 1f of c. And then you have your x2 minus c2 term, partial 2f of x1 t2 minus partial 2f of c. So, or you can put it another way, capital F of x we just take what we just wrote down and divide by the norm of x minus c. For all x that are in this ball centered at C of radius r, well, except the point C in the middle, but we know what f is at the point in the middle. It's just 0, so we don't have to worry about that point. There is one case where you can't apply the mean value theorem. That's it if you pick x to be a point that's either directly above C, so you're going straight up, or directly below C, or directly to the right of C, where you're going straight across. in those cases, one of these differences is going to be 0. So let's notice that if x1 equals c1, then we take t1 to be x1 to be c1. So in this case, x1 minus c1, partial 1f of t1 c2. Well, I don't care what that partial derivative is. We just put a 0. It's just 0 here because x1 minus c1 is 0. So, and that's okay. That is indeed equal to this difference up here. If x1 is the same as c1, those are indeed the same thing. And similarly, we can take t2 to be x2 and c2. So this formula is true even in these very special cases where you can't technically apply the mean value theorem. The reason I wanted to emphasize that is that note that either T1 is equal to C1, T1 is coming from the mean value theorem, so it's between C1 and X1, or it's between X1 and C1 in the other direction. We don't get to pick which side of X lies on. But the fact is, in any case, the difference between T1 and C1 in absolute value, it's less than or equal to the difference between between X1 and C1. In the mean value theorem cases, it's strictly less than, but in the T1 equals C1 equals X1 case, they're both 0, so it has to be less than or equal to. So put that together, you can show that the distance from T1 C2 to C, that's less than or equal to the distance from X to C. And the same for our other special point. All right, and now we are going to apply the continuity of our partial derivatives. So where were we? We've seen that there's some ball centered at C contained in our set X, our domain X, and we've seen that if X is any point in that ball except the midpoint, then we've got this formula for capital F of X, where it's got these two funny points, T1, C2, and X1, T2. And we don't know much about them, but we know that they are also in the ball, and that, in fact, they're closer to C than X is. So now we're going to show that F is continuous at C. And then the proof of claim. We're going to pick a positive number epsilon. And then there is a delta 1 greater than 0 such that if X minus C is less than delta 1, then partial 1 f of x minus partial 1 f of c less than epsilon over 2. Actually, why don't I make this a y instead of an x, because we're going to be applying it to x1, t2, and t1, c2, and not to x. And similarly, there is a delta 2 greater than 0, such that if y minus c less than delta 2, then partial 2f of y minus partial 2f of c is less than epsilon over 2. And now we're going to let delta be whichever is the smallest, delta 1, delta 2, and our r, we're just going to insist that we have to be inside this ball where we've done all our work already. And so then if the distance from x to c is less than r, well, first off, if x equals 0 for continuity, x equals c for continuity, you have to actually look at the midpoints. But that's usually fine. Then f of x minus f of c, that is certainly 0, is certainly less than epsilon. If x is not equal to c, and x minus c is less than delta, then f of x, well, minus f of c, but f of c is 0, so we won't worry about that. That's less than or equal to x1 minus c1 over the norm of x minus c, which you all should be able to see is less than or equal to 1. And then we put the absolute value, partial 1f of, what do we need here, t1, c2. And then we have our second piece. And then if you remember your formula for the distance in Euclidean space, x minus c, it's x1 minus c1 squared plus x2 minus c2 squared square root. Each of these quotients here is at most 1. And then by our assumption, by our definition of delta 1 and delta 2, these two pieces are each less than epsilon over 2. That's because if x minus c is less than delta, then these distances, they also have to be less than delta. So this is less than epsilon. So that proves the claim. That shows that f is continuous at c, and in fact, this completes the proof. So we have shown that f of x is f of c plus a linear function of x minus c plus norm of x times c times this function big F, which we've just shown is continuous at c, and we already knew by definition is 0 at c. So we are done. The next thing we'd like to do is prove this classical result that the only way you can have derivative 0 is to be a constant function. This is a little bit more involved than in the one-dimensional case, so we'll prove this first in a ball, and then we will move on to more general sets. So let's let x be an RP, r a positive radius, and f a function from the ball centered at x of radius r, mapping to the real numbers. And suppose that df of y is 0. And what does that mean? That is df of y, that's a linear operator. If you feed in any vector v is 0 for all v in RP, and this needs to be true for all y in our ball. Then f is constant. And let's write out the proof of this. Let's let z be an element, be a point in our ball. And then we'll specify that z is not our middle point. And our goal is to show that f of z is equal to f of x. Obviously, f of x is equal to f of x, so we only need to prove this for z other than x. So we're going to suppose that z is not the same point as x, and we will show. Let me tell you where this is going. This is going to f of z equals f of x, and thus f is constant. We could do this with partial derivatives, but I don't want to do that. Partial derivatives are either really convenient or really annoying, and this is one of the really annoying cases, so we're going to do directional derivatives instead. So we're going to define the following function. Define g of t, that is f of x plus t times z minus x. For all t in the interval from 0 to 1. So g is now a function from this closed interval to the real numbers. And then let's think about some properties of g. So what we're doing here is we've got our point x in the middle. We've got our ball around x of radius r. We've got our point y in our point z in here somewhere, and then we just draw. Essentially, we're drawing this line, this straight line from x to z, and we're computing what f is along that line. So the first thing to notice is that let's give this a name. We'll let gamma of t be x plus t times z minus x. And then gamma of 0 is our midpoint, gamma of 1 is our target point z, and if t is between 0 and 1, then gamma of t is a point in our ball. So we have that. It's differentiable df of the point gamma of t is equals 0. That is, it's the linear operator that just spits out 0 no matter what your input is. So we have that g of 0 is f of x, g of 1 is f of z, and that means that our goal, what we want to show, is that g of 1 is equal to g of 0. That's where we're going with this. So let's list off some properties of g. G, as we have seen, is a function from 0, 1. Gamma takes you to RP, F takes you back to R, so we can use all of our material from chapter 1 and chapter 2. Now, F is continuous because it is differentiable. That is by a theorem. That is theorem 6.2.12a. Any differentiable function is continuous. Gamma is continuous by theorem, not theorem, example 5.4.6c. It's a function from the real numbers to RP, and each of its components is clearly continuous. So by a proposition 5.4.4, G, which is the composition of F with gamma, is continuous on its entire domain, 0 up to 1. All right. And we also claim that G is differentiable, and we're going to use our section 2.3 results to show it's constant. So let's grab any 2 points in a domain. T is going to be an interior point. Then what we've got is that G of S, that's F of gamma of S. Now we can use our formula for the derivative of F. That's F of gamma of T plus dF of gamma of T. And then that's a linear operator, so we have to plug something into it. We plug in gamma of S minus gamma of T. And then we add to that this norm. And then we put our big F of gamma of S at the end. And then we can say a little bit more about that. F of gamma of T is just G of T. And then dF of gamma of T, we remember, this is 0 everywhere, so I don't even have to write that down. I am going to go ahead and write 0 times S minus T. It's just adding a 0, then an S minus T. And then the distance from gamma of S minus gamma of T, that's S minus T times Z minus X. And then F of gamma of S. And then we're going to let big G of S be the norm of z minus x, which now as far as s and t know is a constant, f of gamma of s, g of t is z minus x, f of gamma of t. Since this is the f coming from the df of gamma of t, this must equal 0. And also, f is continuous at gamma of t by definition of derivative, so g is continuous at t. So we've got that this looks an awful lot like our derivative equation. So we've got that g is differentiable in our strange new sense. dg of t of any num of s minus t is now 0. So by proposition 2.2.9, remember this is the proposition that says that our strange new derivative is the same as the derivative you know and love, g prime of t equals 0. And so there's not much more to this. So by our chapter 2 results, corollary 2.3.6 in particular, we've got that f of x, we've got that g is constant, so f of x is g of 0, is g of 1, is f of z. So the conclusion is that f is constant in the ball centered at x of radius r. We can do a little bit better. So here is proposition 6.2.18. It's a more general result, but we needed the lemma to prove it. So we're going to have a domain in RP be open and connected. So section 5.6 is coming back. Let's let f be a function whose domain is from x to the real numbers, and suppose that df of x equals 0 for all x in x. And the conclusion is that then f is constant. You don't happen to be in a connected set, then what f will be is constant on each connected component. And let's write out the proof. So the first thing to note is that f is still continuous because differentiable functions are always continuous. So now, if x is empty, there is nothing to prove. Otherwise, let's let x naught be a point in x, and we're going to let E be f inverse of x naught. That's all the points in x where f of x naught Sorry, that's all the points in X that get mapped to the same value as X naught. And we remember that since F is continuous, the inverse image of a closed set is closed. This singleton set, sets with only one number in them, f of x naught is closed. So by proposition 5.4.3c, E is closed. Or at least relatively closed. In X. It might not necessarily be closed in RP because X, after all, is an open set. So now let X be a point. Let's let Y be a point in E. There is a R greater than 0 such that the ball centered at Y of radius R is in X. Just because X is open. And then F is constant on this ball by our lemma. So that means that f of z equals f of y equals f of x naught for every z in our ball. So our ball is a subset of E. So E is open. It's not just relatively open, it's fully regularly open. And so we've seen that E is a subset of X, is relatively closed and open. And X naught, our point we picked, is in E, so E is not the empty set. So E is in fact all of X because X is connected. So we have that f of y equals f of x naught for all y in E. And that is all there is to that.